So here we are talking about inferences from two samples. So we're going to be doing hypothesis test with two samples. And what we're trying to do is talk about the differences between the two samples. So we're going to, in 9.1, we're going to be talking about proportions. And we're going to talk about testing the difference between proportions in two different samples. In 9.2, we're going to be talking about the means. Independent samples, and we're going to talk about what's independent and what's dependent. We're going to talk about testing the difference between the means small independent samples, that's going to be the normal, and then large independent samples. Now your author makes this one very easy. He basically says test them all as small samples, which makes sense because remember that the t distribution, as your distribution gets larger, what does the t distribution approximate? Z-score. So basically you should have very little error involved if you are testing a large sample using your t-score chart. You should get a pretty good approximate. So your author says, hey, don't even worry about it, but I will show you where you can, and it would be probably good to compare the difference between the two answers. But we may get to do that in class. But basically, your author uses t-test all the way through here. And then 9.3 is dependent samples. And matched pair samples, we're going to talk about that a little bit. So we've got three categories to go through. And here's our big idea here. We're going to be testing a claim made about two population proportions and constructing a confidence interval estimate of the difference between the two population proportions. So, like I said, we're not going to focus real heavily on the confidence interval. We are going to do it, but it's not like the major goal here. Really want to work on the hypothesis testing the most. But both of them are going to be done on a calculator. So they're going to be very similar. Conduct a hypothesis test for a claim about two major, this is our major focus, this is our minor focus. So now this one is this is right in your book. This is our notation about proportions. P1 is going to be the population proportion from the first population. And then we got to have the same, we're going to have a corresponding P2 would be the population proportion from the second population. We got an N1 is the first sample size and N2 is the second sample size. And then we got the Q1 hat is going to be 1 minus the P hat. So basically we've got the sample proportions. So we got the true population proportion and then the sample population proportion for both. So those are just the terminologies there. And then we've got pooled sample proportion. Now pooled samples are going to occur regularly in your proportions. So when we're talking about proportions, we don't have to worry about when to pool and when not to pool. We're just going to pool. In fact, your technology for proportions doesn't even ask you. It does it for you. But the pooling is inside your technology for proportions. Okay? And so here, when we're doing hypothesis tests for proportions, we're always going to consider only test having a null hypothesis of P equals P2. So basically, P equals P2 is our original option. Remember the hypothesis, the null hypothesis is always the equal situation. So the estimates of P1 and P2 are combined to give us that pooled p-value, and that gives us the best estimate. So it's an estimate, just like our x bar was an estimate of our mean, and our p hat was a good estimate when we had one sample. Now we're going to do this pooling to get a good estimate of the p-value. All right, so now we're going to look here, and it says requirements to use a two-sample z-test for proportions. On proportions, if you look, I'm trying to get you to see the big picture here. if you look over here under proportions and you're on chapter 9, go all the way to chapter 9.1 and you look at the end of the section, okay? And before they give you the homework, remember your book always gives you this little technology blurb right here. So look on page 422 if you have your book. 422 is right at the end of 9.1, okay? And it gives you the keys here. So I'm going to show it here on the thing. So right here on your little video is page 422, and it gives you the technology for the 9.1 section. If you look down here to our TI, okay, and you can see there, do they ever mention anything besides a z-score? Right? You look at the technology in your book, and it's the 2-prop z-test and the 2-prop z-int. So if we're dealing with proportions, we have two tests. 2-prop z-test, writing it on the board here, and 2-prop z-int. Now on your homework, on your My Math Lab, you will need to use this, but you will see that the two are set up exactly alike. They take the same data, it's just that this one is going to give you back a p-value and a z-score, and this one is going to give you back a test statistic and a p-value, I think, and this one's going to give you back a confidence interval. Okay, so that you have that to do your homework online. Okay, so the sample proportions, so these are our what? Requirements. We always have to make sure our requirements are met. The sample proportions are from 2 sample random samples. Okay, the 2 samples are independent. We're going to talk about independence, but samples are independent if the sample values selected from one population are not related to somehow or naturally paired or matched with the sample values of another population. The 2 samples must be large enough to use a normal sampling distribution. For each of the 2 samples, remember, when we're talking about proportions, we're talking about binomial, aren't we? We're talking about binomial trials that we can assume we're going to be able to use the standard normal because we have a large enough population. So our key was that the sample size times the p-hat is going to be greater than or equal to 5, and the sample size for the q-hat is going to be greater than or equal to 5. So here, when you're doing those, we'll see some examples of how we do those there. So it says for each of the 2 samples, right? So you've got 2 different samples you've got to do that test on. So then, if these conditions are met, then the sampling distribution for p-hat 1 minus p-hat 2 is a normal distribution. So they have defined the normality of the situation, okay? And so our mean of this distribution would be the p-hat 1 minus p-hat 2. So we're doing a sampling distribution here. And a weighted estimate is going to be our pool p. Okay, so they're defining the whole situation. The standard error, they give you a formula for that. We're not going to have to calculate that. Our technology is going to calculate that for us. We could calculate it. I encourage you to calculate it once just to see that it works and that you're going to get the same thing that your technology is going to do. And I do that for you here as well. Okay, so basically the test statistic is p-hat minus p-hat, p-hat 1 minus p-hat 2. The standardized test statistic, now here is the standardized test statistic. This is taking your data and finding the test statistic. And then we're going to have the pool P and the Q. And then notice here that they're talking about the P bar. So notice they change from p-hats, because this was a pooled estimate, to using the P bar here to determine if our sample size was big enough. So we've got the N1 P bar, N1 Q bar. into P bar into Q bar. Because we have pooled, we can use that estimate instead of the P1 hat and P2 hat. Okay, so now let's go through the big picture here. So we're going to state the claim. We're going to determine our H sub O and H sub A. We're going to determine our level of significance, alpha, should be given to us, otherwise we use 0.05. Determine our p-value or our critical values. Use your technology. It's going to do it for you. Okay? Determine the rejection region. You're going to determine your rejection region from your what? Your significance level. We've already done that. Okay, we did that a lot when we were in 7, right? How to find a level, use your level of significance to find your rejection region. So then, find a weighted estimate of P1 and P2, okay, which that's their P bar there. That's your best estimate of your proportion. And then you're just verifying that you can do this test, okay? That's your qualifications there. And then here is your standardized test statistic. This is the one that you could plug in and crank out by hand, but you will get the same thing if you put it in a calculator. Since we're doing the proportions right now, we're going to use the 2 proportion z-test. Okay, we're doing proportions, so there's only 2 choices for proportions if we want a confidence interval hypothesis test. Okay, and I'll show you some of those on the screen. And then make a decision, either to reject H sub O or fail to reject H sub O, and then interpret it into words, like we did in chapter 8. Okay, so Connecticut and New York, I think, is supposed to be there instead of New Year. New York are contiguous states, both having laws that require front and rear license plates. The proportion of Connecticut illegal cars with rear license plates only is 239 divided by 2,049, or 11.7%. The proportion of New York illegal cars with rear license plates only is 9 out of 550, or 1.6%. The sample percentages of 11.7% and 1.6% are obviously different, but are they significantly different? Okay, so here's our data that's lined up for us. So we have Connecticut, New York, use a 5% significance level, they give it to us, and the p-value method to test the claim that Connecticut and New York have the same proportion of cars with license plates only. Okay, so here we're going to do our little requirement check. Do we meet the requirements? So I'm going to, basically the 2 samples are simple random samples. We got to trust the author for that. The 2 samples are independent because the cars in the samples are not matched or paired in any way. Some are from Connecticut, some are from New York. Okay, let's consider a success to be a car with a rear license plate only. So for Connecticut, the number of successes, the number of failures, they don't change depending on what the other group is doing, right? And there are 9 successes and 541, and they are both at least 5. Okay, so basically the requirements are satisfied. So now we state the claim, and we come up with our our H sub O and our H sub A. So we're going to say that the claim is that have the same proportion of cars, that the 2 P's are the same. Okay, if P equal P2 is false, then P1 does not equal P2, and that would be our alternative hypothesis. So we got P1 equals P2, P1 does not equal P2, and we've defined our situation. Okay, so now we're going to come over here. The significance level was specified as alpha is 0.05, so we will use alpha as 0.05. And then we're going to use our technology. We're going to go and use our technology. This step and the following step can be circumvented by using technology. Circumvent it. Use your technology. Get comfortable with this process. Okay. See the display that follows this example. If not using technology, we use the normal distribution. That's your z-chart, right? As the approximation of the binomial. So we're going to go to stat, we're going to hit test, we're going to go to a 2-prop z-test. All right, so everybody go there, and we'll do this in a minute. So here, I'm calculating it out by hand. Okay, we estimate the common value of P2, so there's my pool, the one, P. Now, I do need to do this in order to determine if I can use a z-test, okay, or a t-test. I have to be able to say that they meet normality standards. In order to do that, I need to be able to do this much I have to do this without my technology, because I need to know, do I meet qualifications? And you have to show that on your test. Did you meet qualifications? And you're going to have to do that math, okay? But then, this is what you're not going to have to do. You're not going to have to use this because you've got it on your calculator, okay? You don't want to do that without. So I did it for you, but I want to show you that you're going to get the same thing from the technology, okay? So I did it by hand just so that you could see it. So then you end up with a z-score. This is your test statistic. Your standardized test statistic is 7.11. Is that unusual? Okay, think of it. Huh? Yeah. Remember what we say about 2.5 beyond? It's going to be unusual. No matter what kind of criteria we're using, that's unusual. Okay, so, but let's look at it. So this is a two-tailed test. Why is it a two-tailed test? Because what was my H sub A? Not equal to. When my H sub A is not equal to, I have a two-tailed test. Okay, so this is a two-tailed test because we had not equal to for our H sub A. Okay, so the p-value is twice the area to the right of the test statistic, z.11. Okay, now, if you looked at your z, if you were doing this without technology, and you looked at 7.11, it's going to give you 0.9999 as the value to the left of the curve, okay? But if you were doing it with technology, you would say that's the area. It would give you back that value with technology, which we're about to do in a minute. Okay, so the p-value is actually less than, even if we doubled it, once we double it, it's still less than 0.0001. Okay, very unusual. So then we're going to say our p-value is way over here in the tail. The test statistic, 7.11, is our, so our critical value is not that test statistic. I think this slides a little bit off, but our test statistic is in here. Our critical value would be right there, okay? So basically, I think this slides a little off. It should have the area, the level pointing inside there. But p-value for a two-tailed test, double this area. So we find what the p-value is to the right of 7.11. That's our p-value. And then we double that area and we compare it to our 0.05. Okay, and because the p-value of 0.0000 is less than the 0.05, we reject the null hypothesis. And then, so basically this is, we must address the original claim that Connecticut and New York have the same proportion of cars with rear license plates only. Because we reject the null hypothesis, we conclude that there is sufficient evidence to warrant rejection of a claim that P1 equals P2. That is, there is sufficient evidence to conclude that Connecticut and New York have different proportions of cars with rear license plates only. Okay, so they're concluding what they determined. Okay, now this one is the same problem, but it's done on stat disk. Okay, so what I want you to do is let's take the same data and let's do it on, since we don't have stat disk on a test, let's do our, notice how the stat disk gives the hypothesis information, but it also gave the 95% level of confidence interval. So, Here, it's an interval, and it's a two-sample confidence interval here. And so our equivalent of the stat disk is going to be these two right here. The cool thing is that once you set up your hypothesis test, your confidence interval test is set up for you by the calculator. You don't have to set it up twice because your calculator figures you're using the same data for both since they're so interconnected. So that's pretty cool. So what we're going to do is we're going to go back to our original. Oh, actually, I set it up for you here. Now, let's go back to our original and look at our original data and plug it in. Okay, so we go back to this. Okay, this is what we need. So we're going to go to prop ztest. So we're going to hit stat, and then we're going to go over to calc, and we're going to go down to prop ztest, and we're going to hit enter. Okay, now we're going to put in, notice it says x1, n1. This is your x1, this is your n1. Okay, that's your x2 and your n2. So, no, excuse me. This is your n. This is your total. I misread that. This is your total. This is your n. This is your n2 over there. So you're going to click those in. So we're going to say x1 is 239. We're going to say that n1 is 2049. And we're going to say that x2 is 9. And n2 is 541. And then we're going to use the not equal to P2. They've got less than, greater than. In other words, what are they asking you? Do you want a two-tailed test, a one-tailed test left, or a one-tailed test right? Okay, so since our problem was, okay, our claim was that they were equal, and we're saying the alternative is they're not equal, we're using a two-tailed test, so keep it on not equal to, go down and calculate, and we get this screen. So I get P is not equal P2.
Is it 541 or should it be 550?
Which one?
Or is it 550?
Oh, 550. Excuse me. You're right. I entered it wrong. So I got to go back and do that again. Okay, so yeah, I did 541. So 550. Thank you. So now I recalculate, and it should match the screen that I have here, which I did it on the calculator right there. Okay, so what you should be staring at is right here. And since that's very fuzzy, I will come over here and show this on here. But that should be what you see on the screen. You see what you see on the screen? Okay, so then notice you have a little arrow that's telling you to press down to see the rest of your information. So go ahead and press down on your calculator, and you see this screen, which gives you P1, P2, and P hat. Okay, now that P hat is your p-value. That is your p-value that is right here. So your p-value is what? 0.095421. Okay, so your calculator gives you back the p-value. You had to do nothing but enter in your data, and you get back your p-value. All right, so now remember that being able to go to the, what if you're asked, and I know on your online homework in chapter 9.1, you're asked to find some confidence intervals. No biggie. Keep your data, do your hypothesis testing first. Now go to second prop z int. That's your confidence interval. So now we're going to go to stat, over to test, and go to second prop z int, which you have to scroll down a little bit to get down to second prop z int. Hit enter, and your data should already be there. Okay, now your confidence level here is 0.95. My last confidence level was 0.9, so I'm going to have to change that to 0.95. And then I go down to calculate, and I get what? What is your level that you get? 0.0828 to 0.11776. And you have a confidence interval for your population proportion. Okay, so there they have it right there. And here I have it a little bit clearer on my screen. There. Okay? So, questions. All technology driven there. That's your 2-prop-z int. And you're going to use that for your interval, confidence interval, when you're asked it, okay? So like I said, the big deal is hypothesis testing, but if you're ever asked a confidence interval, just jump over there to that prop. I think they only ask you the confidence interval on the proportion portion of this section. Jump over there and they will have already filled it into your, did everybody have those pre-filled out for them when they went over to the prop Z? It wasn't already filled out for you when you changed over? Mine were.
The props,
yeah. Mine were pre-filled by my calculator when I went over.
Did you use 95% or for the CLO?
I used the 0.95 because they told us to. All right, so now look at this one. Suppose we want to do the critical value. Look at what we got back from let's go back to our test here. So this was when we did the prop Z test. What did we get back? We got a Z, that was our test statistic. Our data's test statistic, okay? And then we got the p-value, okay, so this one here is this one is the p, and then this one, so this one right here, 1 minus that is this. So look how little it is. Remember, it was way out there. So that's your p-value, which you would double. And then, this is your data's right here. So this was your original proportions. These were your original proportions, and then this one was your pooled proportion. That, I think I said it backwards before. But your p-value is this little bitty thing. Notice that e to the negative 12? Okay, it's itty bitty because it's way to the right of 7.1 or whatever it was. Okay, so this is your z-score and your p-value come up at the very top of your screen. So now if you're doing a p-test, you compare your p-value. Since it's two-tailed, you double that. And then you compare it, which is basically 0.0000, right? And you compare it to your alpha. If you're doing a critical value test, you take this z-score, which is your test statistic, and then you compare it to the z-score that goes with 95%. Okay, so basically we were to have an alpha of 5, and the alpha of 5 was to be split into 2 tails. Okay, so when we look at it, this is talking about that right here. How do we do a critical value method here? They don't give us back this critical value. We have to determine that based on what we know. Now, for the most part, these critical values are going to be the same ones that are in your bottom of your Z-chart down here. Remember, common critical values down there? So we're looking at 95%. And guess what it says? 95%, 1.96. So all we have to do a critical value test is go get the critical value, take the Z test statistic that we just obtained from our technology, and compare the two. Okay, so this starts our critical region, and because it's two-tailed, it's in 2 tails. Remember, this chart down here is a 2-tailed chart because this was a confidence interval chart. Okay, confidence interval is in 2 tails, isn't it? So we had, this one is the right number to use. We compare, 7 is way into that rejection region, isn't it? Because it's way past 1.96. So we reject the H sub O. Okay, so here 1.96 was our critical value. Our test statistics way in the rejection region, we reject H sub O. So we should be able to do that both with a p-value and comparing it to the alpha, and a test statistic and comparing it to our critical value that we get from our charts. Okay? So what do we do when we get bad samples? So what do we do if I give you something on the test that you don't know how to do because you have, it doesn't have enough, it's not normal, something doesn't work in the requirements, what are you going to do? Okay, we don't worry about this stuff. You just say no way. I can't do that one because the data is not there for me. It's outside the scope of this class. We're not worried about all this other stuff they're talking about here. We're just not. Okay, we don't have time to be worried about that. So, now notice they give you a p-hat. In this example, they give you a p-hat. What does your technology give you? Your technology wants a what? Your technology wants an N1 and a X1 and a X2 and an N2. Isn't that what your technology wants? But they don't give you that. They give you a proportion. They give you a p-hat. So we have to calculate those to be able to go into. So basically what we do is we come here. What is an X1? It's going to be the number in my sample times that proportion that is for that sample. So I multiply them together and I get the X1. I get the X2. It's just a multiplication that we have to get those. And then we pool them. And then we're going to do what? We're trying to figure out, hey, do we have normality here? Can we do this test? So you're still going to do this by hand because you need to know, you've got to use this pooled value to show me that you are legit in doing this test. That part you are going to need to be able to do by hand, okay? So then you're going to say, yes, all the qualifications are made, okay, so now I'm going to, okay, I'm not sure why I did that. But anyway, here is the by hand calculation, but we're not going to do it by hand. We're going to go use the what? We're still in proportions. We're going to use the 2-prop z-test. Okay, so here is the our 2 ends, and we have our, since we're doing a 10% alpha is what they specified, we're going to put it, since our H sub A is not equal to, we're going to put it in 2 tails. So we end up with 0.05 in each tail to define our rejection regions. Okay, and our test statistic we just calculated on the last page is 2.73, and our 2.73 is to the right of the critical region that goes with the 2-tail here. So 1.645 is the critical value that goes with 90%. Check it, am I right? So you go back over here to your little critical value chart right here. Right, your little critical value chart right there, and you check 90%, 1.645 on a 2-tailed test. So then you can do this one without technology because you've got enough to go and just say, well, 2.73 is to the right of 1.645. It's in the rejection region, so I reject H sub O. Okay, and I did the same thing using the z-test. Entering all the thing, and I get 2.73. And then right under it, I get the p-value in case I wanted to do the p-value method instead of the z critical value method. Okay? So everybody's seen how easy this is once you get the big picture. It's not hard. Okay? So now there's the second part there. And another example, and we're running out of time to do examples. I wanted to show you the big picture. More examples. More examples. And, okay, so now, look what it says here. So that's all we do with proportions, okay? So your technology is your 2-prop z-test and your 2-prop z-int if you need to give a confidence interval, which you will in some of your 9.1 homework. They'll ask you the confidence interval that goes with this test. They do everything for you, including pooling the data. All you have to do is pool the data at the beginning so that you can determine, hey, can I do the test? Am I not qualified to do the test? Do I have the requirements met? Do I not? You have to pool the data for that. You have to get your P-score. So practice, practice, practice using these functions. So we're almost out of time. I'm going to just jump through some of the others. I will put all the videos online. But the big thing is, folks, is that you're going to have to get so proficient with this. Okay? Now, look at, we're going into the second one where we start to talk about the means, independent samples. Your author uses the t-test for both of these because he's saying, hey, your large sample t-test is so close to your z-test anyway. Just go ahead and use the t-test and you're going to get the same thing, all right? So when you do get to that, you might want to do it both ways, but the difference is going to be so negligible that for our purposes, it's going to be fine. Okay, so basically this part is, the big thing is learn what is independent and what is dependent. Two samples are independent if the sample values from one population are not related to or somehow naturally paired. Okay, two samples are dependent if this are matched, and this is the last section. This was the 9.3. When you have matched pairs. It's just a little bit different, and I'll put the video out so you know what to do with matched pairs, but it's a very short section, okay? And then it says where the matching is based on some inherent relationship, okay? So here is a picture of independent samples and dependent samples. Usually, independent samples are going to have two completely different numbers in them. They're usually taken from different states or different types of cars or whatever. They're not related. So you can do two independent samples that have no matching whatsoever. In fact, it's kind of intuitive. We have two different sets. These are dependent samples where the two sets actually match and go together in some way. Okay, so here it says classify the pairs of samples as independent or dependent. So weights of 65 college students before their freshman year begins, weights of the same 65 college students after their freshman year. Are they connected? Yes, we're using the same students. Okay, so that would be paired data, right? They're dependent on each other. They are paired with respect to each student, okay? Scores of 38 males in a psychological screening test for attention deficit hyperactivity disorder. Scores for 50 adult females on a psychological screening test for attention deficit hyperactivity. Different people, different sample sizes. They may be taking the same test, but hey, they're two different samples, okay? So they are independent samples. We can't match those up. They're not even the same size sample. Okay, so not possible to form a pairing between the members of the sample. The sample sizes are different and the data represents scores for different individuals. Okay, so now we're about to go into this, but I did read online, so like if you did, if you were doing a test on husband-wife couples and you said, okay, are they paired? Well, yeah, even though they're not doing the same thing on the opposite sexes, but they are linked to each other and they were connecting the data together. So they were paired because they were husband-wife sets, okay? Even though they separated them, they were pairing the husband and the wife together, okay? So now we're starting into inferences about means. We're out of time. What I want you to do is I'm going to go and put these PowerPoints. I'm going to stop the PowerPoint here on the end of proportions, and then I'm going to start